Okay, so it's 5 p.m. Let's start. Oops. So before we start, hopefully most of you have at least gone through this tutorial sheet. And there's a very difficult question, which is question 4. Before we start, just want to ask you guys if you prefer I go question 4 at the beginning or do it in the end. Any preference? No? Okay, so I will leave it to the end. Let's quickly go through the easiest part, and then we will do the question 4. All right? So for the question, oops, I put it. Yeah, for the question 1. It's asked, we have a kind of U-shaped tube with water in it. So we have it, the water level higher. Oops, but, we have water level higher at the left-hand side. The height is 20 centimeter. Lower at right-hand side, the height is 12 centimeter. It says it's rotating regard to a axis. It's kind of asymmetric, so we have 10 centimeter at the left and 5 at right. So it rotates in angular velocity of omega. So it asks what omega is. Right, so this one is actually pretty straightforward as long as you remember this equation. The pressure equation regarding to the radius. This is the equation in your textbook. I think it's 2.43. If you cannot remember it, go back to check your textbook. So this question basically focuses on this equation. So here we have a relationship of, so when it's rotated, how the pressure generated by the rotation. So it's a kind of, sorry, excuse me, if you have something to discuss, would you mind to do it afterwards? All right. So yeah, so we have a relation now between the pressure and the radius. So this is the pressure caused by the rotation. All right, so now we want to get exact pressure. So we want a pressure in relation of radius. So not this partial derivative form. So what do? We do the integration. So here, this equation, partial P over partial R equals rho times U squared over R, can be transferred into partial P equals rho times U squared over R times partial R. Right, and here, since in this question, we are considering about the angular velocity. So we replace this bit by U equals omega times R. Well, this is small r here. So this is equal to, very directly, we have omega squared times R times partial R. So then we do the integration by integrate partial P should be the same as integration of rho times omega squared times R partial R. So this is pretty straightforward. So we have P equals to half rho omega squared times R squared. Right, so we have a relation between P and R, direct relationship. So now we know the force, we know the pressure generated by the rotation. So then we have a pressure difference, pressure 2 minus pressure 1. This pressure difference is, first of course, since it's rotation, so we have a difference on radius. So this causes a difference in pressure. So that will be half rho omega squared times R2 squared minus R1 squared. So this one should also be the same, should be equivalent to the pressure difference caused by the height of the surface, right? So by the depth of the fluid. So this one must be times G times Z2 minus Z1. So we have Z2 as 20 centimeters. We have Z1 as 12 centimeters. We also know the R2, which is 10 centimeters, and R1, which is 5 centimeters. We have density cancelled. We know the gravity, so it's pretty straightforward to get angular velocity, which is 14.5 radius per second. The answer on the tutorial sheet is the unit is not correct. It should be 138 revolutions per minute, not per second. This is the final answer. Is there any question? Yes, please.
Would we be getting the same amount of marks if we use that same old equation we found in the book of P is equal to P0 minus rho GZ plus...
Yes, you will. So as long as you know where it comes from. Well, you not necessarily exactly tell me which equation it is, but if it comes from the book, then you definitely have free to use it. There won't be any.
That was 2.43. What is 2.43?
It's equation 2.43. You go to the textbook. It's roughly at page 80 to 90. I can't remember exactly. Any other question? Okay, so let's go to the second one. Okay, so the second one is a block fully merged. So we have water on the top. Well, we have a steel. We have a steel, and it's half merged in water and half merged in mercury. So water is adding to oxygen, and this is the mercury. All right. So here we can. So it asks. So we have this is as A and this part. So in mercury is B. So as the ratio between A and B. All right. So here we assume the width of this block as L, and the width and the depth as W. Anyway, they will cancel in the end. So then we can have the buoyancy from the water as the density, which is L times A times W. So this is the volume in the water times water and times gravity. And then we plus the buoyancy created by the mercury, which is L times B times W equals density times gravity. So the sum of this should be the same as, since it's in balance, so it should be the same as the weight of itself. So it's L times A plus B, L times A plus B times width times density times G. All right, so we have G cancelled. Here the one message missed. Well, usually you will definitely be given in the exam. So that is specific gravity of mercury should be 13.56. All right, and also we have the specific gravity of steel, which is 7.85. So then we know that here I have this as, well, this is water density. This one should be the 13 times 56, density of water, and this one should be 7.85 density of water. So we have water cancelled, gravity cancelled, and width cancelled, L cancelled. So this gives us A times 1. So this, since we cancel the density of water, so A times 1 plus B times 13.56 should equal to A plus B times 7.85. So this is pretty straightforward. We can have the ratio between A, B as 0.834. Any question for this one? Yeah, please.
So the volume of the steel block can be L times W times A plus B.
Yep.
Thank you. So.
Yeah, is that all right?
Yep.
Okay.
It is.
Cool. Yes, please.
What does the A by B stand for exactly?
So it's the question asks what will the ratio of the distance A and B. So so A is the part in water and B is a part in mercury.
So it's like a ratio of the two distances.
Exactly. Okay. Any other question? No. Okay. So let's go to Q3. Well, good. We are still ahead of the agenda. Yeah. So here, this one, the description of the problem is a little bit complex. So we have flow with density, volume rate, and velocity. And then it hits a disk and an angle of theta. So part of the flow goes upward along the disk. So this is 1, this is 2. Goes up as the flow rate is alpha times Q. Oh, sorry. So yeah, and the velocity, right? And part of them goes downward, so it's 1 minus alpha times Q, and we have a velocity, the same velocity. So the velocity doesn't change. Okay, so on the disk there are two forces. So one is the friction. It's called Ft, and the other is a normal force. We call it Fn. Right. So the problem tells us that Ft equals 0. So and asks us to find two things. So one is under condition find alpha. So alpha should be a function of alpha should be a function of theta. So find the alpha in function of theta, and also find the Fn. Right, so ask us to find two things. So we consider the flow here. Okay, so here we consider the flow. It can be considered in two directions, so in the tangential direction and in the normal direction. So it's natural for us to decompose the incoming flow into these two directions, right? So don't forget the direction since we decompose a vector. So we need to keep its direction and make sure it's clear. So here we have this angle as theta. So that means we have this angle as theta. So that means we have this angle as theta. So the part in normal direction will be rho times should be Q times sine theta, and the tangential direction will be Q times cosine theta. Right. So then we can have the equilibrium. So in the first, it says the tangential force is 0. So it's quite direct. We can say that in the tangential direction we have the incoming flow with a momentum equation with a momentum as density times volume flow rate. So this gives you the mass flow rate, and then times velocity. And then don't forget this cosine theta, times cosine theta. And should be the same as the the end condition, which is we have alpha times q times rho. This is the going upward in section 2, and then times v minus, so it's in the opposite direction for the going down part. So that is, minus 1 minus alpha times q times v. Right, so here we have the density. Oh, sorry, I forgot the density here. So first we have density cancelled. We also have volume cancelled.
Excuse me for a second. Isn't it supposed to have an angle as well for the other one?
So here we only consider the force. So here maybe I write it in a different way. Okay, so let me do it in a different way. So if we think we have the sum force in tangential direction, it should be 0. So that is, we have the inlet condition, which is rho times q times v times cosine theta, minus the outlet condition. Outlet condition will be alpha times q times v times density minus 1 minus alpha times q times v times density.
So there's no angle related to this.
Yeah, since we only consider the tangential direction.
Oh,
Right, so we have already considered the angle in the inlet part, so we don't consider any outlet in the final stage. All right, so here we have is, so that we have, again, we have density cancelled, we have q cancelled, we have v cancelled, and then it leaves cosine theta equals to, well, minus alpha minus 1 minus alpha equals 0. So this gives us cosine theta equals 2 alpha minus 1. So that means alpha equals to cosine theta plus 1 divided by 2. So this is, first we got the alpha. And it's the same thing for the normal force. So we still have the normal force, sum of normal force be 0 because it's in a steady state, it's in a balanced state. So the sum of the force will be 0. So this is the same. We have the inlet force as density times q times v times sine theta should be the same as the Fn. The outlet will be the Fn, right? Minus Fn. So this one should be 0. So the normal force is straightforward, will be density times q times v times sine theta. Is that clear? Cool. Any question? No? Okay. Yeah, please.
For Fn, for the sum of the normal forces is equal to 0 is equal to the input force minus this net force, not cosine theta, not sine theta, I mean.
Well, here we only consider the direction in normal force, in normal direction. So that means you need to first decompose the inlet into 2 components. So that is, one is normal and one is tangential. So here, when we consider the force in normal direction, that means the force times sine theta. So think about the coordinate system. So we first do the decomposition and then consider about the balance. Is that all right?
Yep.
Cool.
So the input is equal to, input sine theta.
Yep. Yeah, in the normal direction, that is the case. Cool. Any other question? All right. So let's just skip the question 4 and we directly go to question 5. It's a little bit beyond the boundary. Yeah, so the question 5, where's the question 5? Oops, just a bit more. Yeah, here is a rocket. So we have a rocket has an acceleration of so we have a rocket has an acceleration of az. Well, this obviously it has a gravity of g, and then we have a outlet thrust pumping out the air or the gas, the hot gas, and with velocity we call it v out, and the total mass of this rocket is 1,000 kilogram. The cross-section area A is 300 square centimeter, so that is 0.03 square meter. We have density. This is the density hot gas, exhausted hot gas, so that is 0.4 kilogram per cubic meter. And we have the vertical acceleration as 3 meter per second square. So then it asks to calculate the velocity of the exhaust gas at the thrust. So the first thing is we apply the Newton's second law. This is quite obvious. So we have the sum in vertical as the, so if we consider the rocket as a whole, so it has a mass of m times it's accelerated in az, so it's mass times az, should be the result of two forces. One is a force from by the gas, and then we have a force of gravity. Right, so then, we need to consider the direction, So we assume the positive direction point downwards, then the, so we assume, my mistake. So generally we assume the positive direction pointing upward. So we have the F thrust should be pointing upward to give the proportion of the rocket. And then we have the gravity in the opposite direction. So this is the total force on the rocket that gives it a acceleration of az. So this is obvious. We can find the thrust as m times az plus g. And also we know that since the gas coming out from this kind of hole, it has a diameter of a, and we also have the outflow rate as v out. We also know the density, so we time together. This one is the mass flow rate, and then we time the velocity. So this is the momentum created by the emitted gas. So this one should be the same as the acceleration, as the force, as the thrust force on the rocket. So here in this equation, so then we have, if we look at this equation, it will give us V out equals to Az plus G divided by A times rho and square root. So all the quantities here are known. We know the total mass, we know the Az, we know the gravity, we know the area, we know the density. So this one is easy to calculate. So it's, the number looks strange. 1,033 meters per second. Is that the answer on your tutorial sheet? Yeah, so that's the correct one. I thought I missed a decimal or something, but yeah, so that's a correct answer.
So why did you square root
Because we have two V out here. We have one V out to calculate the mass flow rate and the other for the velocity. Any other question? Cool. So let's move on to the question 6. This one is definitely, well, question 5 is a kind of high school one, so it won't be very difficult to most of you. Yeah, so 6, it requires some, the equation of ideal gas. I assume most of you have covered that. Please let me know if you haven't heard of an ideal gas. So that P equals rho times R times T, this relationship. Hopefully everyone has heard of this before. Right, so this is the equation we rely on for this problem. So here we have a balloon, hot air balloon shown in figure 6 to support the total weight of 1,300 Newton. The ambient air is 20 degrees 1,000 kilopascal, and the hot air is inside is 70 degrees at 100,000 pascal. So as for the diameter. So we first think about, since it asks about the diameter, so we first think about the weight of balloon by, if we calculate by this given diameter. So the weight will be, this is pretty straightforward. So the gas inside, so we call it rho B times the, times the volume of this balloon times the gravity. Right, the volume is quite direct, is 4/3 pi half d cube. Right, so we have the times pi half d cube times g. So this is the weight of the balloon, and then we also can calculate the buoyancy, which is density of air times V times G. So it's exactly the same as above. So it's air. So since we have the same volume, so I have times D over 2 cube times G. So since it has to support a total weight of 1,300 Newton, so that means V minus the, so the buoyancy minus the balloon weight should be that 1,300 Newton. Right, so then if we deduce this by, we deduce this too, so this gives us density difference, which is air minus balloon times 4 pi d cube g equals to 1,300 Newton. So these two, remember we have the relation of P equals rho RT. So it's pressure equals density times a constant times pressure. So that means density equals to a constant times temperature divided by pressure. This one should be in Kelvin. And then we can calculate the density, since we know the temperature and pressure of both air and inside and the hot air inside the balloon. So we know the density of these two, and gravity is known. The result is known. So the only unknown is this. Is this diameter? So it's easy to find the diameter. Yes, please.
I've got a question about the value of R. Is the value of R going to be 8.31?
I don't think so. Here, you need to remember there are several forms of P of this ideal gas equation. So one you talk about is P equals nRT, I assume. So that's different with P equals density. So this is the
I'm just following along with your solution, and I'm still kind of confused about the value of R.
So for value of R, this one you will be given. So this R depends on the equation you are using. So there are different forms of ideal gas equation. You need to carefully select which R it is. And in your exam, you will be given the exact number of R. All right, because for example, if you compare the amount of material and the density, you have a kind of factor in there. So you need to consider that part. Yes, please.
I have a question. Isn't the D supposed to be D divided by 2?
Yeah, d divided by 2, sorry. Is that all right with ideal gas equation?
But what is the value of R we're supposed to use here?
Yes, here you're supposed to use 287.
This is the most we need to do? This is the most significant figure for R?
Yeah, so no, this is not the most significant figure, but you can use 3 here.
Wait, but this is accurate, right?
Well, this is accurate enough for this problem.
Will the value of R be given?
Yeah, definitely. If you have this in the exam, you will definitely be given the R number. They won't let you guess. It's impossible. You cannot find it on your own. Any other question? Yes, please. P equals rho RT, so you have rho, you have RT divided by P. Oh, sorry, here. My bad. Yeah, sorry. It's P over RT. Yeah, sorry. Yeah, I apologize. It's P over RT. Yeah. Thanks for pointing out. Yeah, did I make any other mistake, or if you have any question? Okay, so let's go to the question 4. This is the most challenging one. Very difficult. Actually, this one, I observed a similar question in third year lab. So, well, feel free if you cannot find out the solution immediately. This is not so easy. So here we have a inlet, uniform inlet has a velocity of u0. And we have an object. It goes through the object. And at the outlet, we have a kind of velocity profile. It's u0 on both sides. And the minimum point is half u0. So it asks, so we have the width of B and the length of object as L. We also know the dimension in the wake as is symmetric with L on both sides. So it asks us to find out the drag. Right. So the drag, how to find out the drag? The idea is quite direct. So if we know how the momentum loss of the air, so that must be the same as drag. So the only thing we need to calculate is we compare the outlet and the inlet, and we find out the momentum loss, and that will be the drag. Is that clear for this step? So then, how to calculate this? There are several ways to think about. I will try to explain it. But for any method, we need to define a control volume. So there are different ways to define the control volume. I will define it as this way. So as we can imagine, first the control volume, I wanted to satisfy the mass conservation. So that means we have the same amount of mass in, we must have the same amount of mass out. So that should be equal. That should be equal. Is that clear at this step? So then we can imagine, since we have some velocity loss here, so mass equation, mass flow rate is the Q times, it's density times Q times V, right? So we have density the same. So here, if we have some velocity loss, that means we will have, if we have some velocity loss, so that means we must have a smaller inlet comparing with the outlet. Is that clear at this step? So then a question comes to us, what is this height? So what is the inlet height of the inlet? It's no longer B2L because we definitely have a smaller inlet to ensure the mass conservation. So then what is the H? We define the inlet as H. So what is H? So first step, we want to calculate the H. Here we apply the mass conservation. So mass in must be mass out. All right, so for mass out, so for mass in, it's very direct. So we have the Q equals to H times, well, it's basically the area times velocity times density. And that is, the area is H times B. So we have the height of H and we have the width of B. So H times B times velocity times density. It should be the same as the mass flow rate outside. So for the outside, it's a little bit complex. So we have a profile like this. The peak point is U0. We have linear in between, and the minimum point is half rho 0. So to calculate this mass flow rate, we can divide them by 2. So since it's symmetry, so Since it's symmetry, so we can only consider the top half and then double it. We got the total mass flow rate. So for this bit, for the top half, we have is in the shape like this. So we have half U0 here, we have U0 here. So we can easily find out the relationship. So we have a Y. And here's 0, here's L. Right, so we can easily find the relationship between U and Y. So that will be half U0 divided by L times Y plus half U0. So far, is it clear? Any question? No? Okay. So we kind of know the velocity profile, so we can do the integration, right? So to do the integration, we first do the top half and we double it to it. So it will be 0. We integrate from 0 from 0 to L. So that will be since we already have the relationship of this line, so it's U0 over 2. Divided by L times Y plus half U0. And then times it by Y. So this is H times U equivalent to the H times U. And then we time the B and density. So then we need to do the integration. This is pretty straightforward. So 2 times we can put U0 out, so that U0 times B times density, integration of 0 to L, 2L over 1 times Y plus 1 over 2 dy. All right, so now we do the integration of this bit. This bit there shouldn't be any difficulty. So that will be 4L over 1 y squared plus half y from 0 to L. So this one gives us, if we put L here, it will be 4L, so L over 4 plus L over 2. It will be 3 over 4L. So then we have this one as a whole goes to 2 times U0 times B times rho times 3/4 L. So it's half 3/2 times U0 times B times density times L. This one equals to, if you recall this bit, it equals to H times B times U0 times density. Right, so then you have what we first asked about. We have the H as 0/2 L. So that means, if we recall that profile, inlet, outlet. So here we have L, here we only have a total of 3/2 L. So we have we have a control volume like this. It's kind of expansion from this height from 3/2 L to 2L. Is that clear so far? Yeah, so then we know the inlet mass flow rate, we know the outlet mass flow rate, we can apply the conservation of momentum. So apply conservation of momentum. So for the inlet, we have, so again, we have the mass flow rate at inlet. So to apply the momentum, we just use F inlet should be the mass flow rate at inlet times the velocity at the inlet, right? So the mass flow rate at inlet, we just gone through it, is 3/2 L times B times U0 times density. So it's exactly the same as this bit. And then we need to calculate the outlet one. The outlet one is a little bit tricky, so it's not so direct. So we still recall that since it's still, again, as the mass flow rate, since it's symmetry, we only consider the top half. So again, we have this relationship half U0, and we define it as 1 from 0 to L. So for each dy, we can find out the corresponding velocity at this point. The corresponding velocity at this point should be uy equals to, again, following the relationship. Let me change the color. If we follow the relationship as this one, right? So it gives the velocity profile as u0 over 2 divided by L times y plus half u0. So this is exactly how velocity change in this along this line. Right, so then we do the force at outlet is a kind of integration of y times dy times b times density. It's times dy squared times b times density. Because this one, you can see that as, let me rewrite it in a different way. Okay, so for each dy element, it will be y times dy. This is the mass flow rate. And then you time another u. So this gives you the momentum. We accumulate them together, and then times b times density. So this will be the mass flow, the momentum at the outlet. Is that clear? Yeah. So then this one is uy squared times dy times b times density. So what is uy squared? So uy, we already got it, is u0 over 2 divided by L times y plus half u0. And we have a square and dy, and then we times b times rho. Right, so it's b times rho times integration, this one from 0 to L. Oh, got a mistake. I forgot to time 2 because here we only consider the top half. We haven't considered the bottom half. So it will be the same. So we need to times 2 on both sides. Time 2 every time. So here we have 2 times 2 times, we expand this, will be 4L squared times U0 squared times Y squared plus half L over divided by U0 times Y plus quarter of U0 squared times dy. So we do the integration of this bit. Oops. 0 to L. Right, so this looks scary, but actually it's very straightforward. 2b rho times, well here this is 12 times L squared divide U0 squared times Y cubed plus 4L divide U0 times Y squared plus U0 squared over 4 times Y. Y range from 0 to L. So this gives you 2 times B times rho times 12 divide U0 squared times L plus 4 U0 divided by 4 times L plus, oops, oh yeah, I forgot. I mean it's a U squared here. So it's U squared times L. Right, so this combined together reaches 12 over 1 plus 3 equals 7 over 12. So this gives us 7 over 6 times B times density times U0 squared times L. So remember, we have, this is the F out. We have F in as 3 over 2 times B rho U0 squared times L. Right, so then we have the force on air. So we have air inside, we say it's air. So we have force on air as F out minus F in. So that will be 3 over 2 minus 7 over 6 times B rho U0 squared times L. So that is 6/9, so it's minus 1/3 times B rho U0 squared times L. And then we want to have the drag. Apply the Newton's third law. Drag is the, since this air, the force on air is coming from the object to the air. So we want to calculate the force from air to object, to that object. So that we apply the Newton's third law. So that will be minus F air. So that will be 1/3 of B density U0 squared times L. So this is the final answer. This one is fairly complex, but hopefully Alistair will upload you a video later to tell you how exactly this one is solved. Yes, please.
Okay, so for the volume, we can assume that the volume is equal to the mass that passes through is equal to rho times B times L times U0, right?
Rho times V times, V is velocity.
B.
Rho times B times, well, sorry. It is the last hour of this week, so I'm also a little bit clumsy. So which one are you talking about? This one? Are you talking about this one?
So H is actually. So what's this value
we assume that, so if you still remember the definition of this control volume, so we assume that there's no mass flow outside this control volume. So this is outlet, we want the same mass flow at the inlet. So definitely the inlet width will be smaller than the outlet width. Is that clear?
So H is the height of our control volume.
Inlet of the control volume. We have different height at inlet and outlet. H is the inlet.
So H is the height of the inlet of the control volume.
Exactly. So let me go through the idea of this question quickly. So at the beginning, since we have an object, so we must have some loss of the momentum. So that the loss of momentum is exactly what we want in terms of drag. So what we do is we need to find the control volume to find out that momentum loss. So to define that control volume, we want to have the inlet mass flow rate same as outlet mass flow rate. So here we know the profile at the outlet, and we know there's a reduction in the middle. So that indicates that at the inlet height must be smaller than the outlet height. So that's why we need to find out then the inlet height, what the height at the inlet. So we assume that is h, and we apply the mass conservation to get that h. After we get that h, we can calculate the momentum at the inlet and momentum at the outlet. These are just several integration tricks. So we know the momentum at outlet, know the momentum inlet. We can do the deduction and find the momentum loss. The momentum loss is the force acting by the object to the air. So drag is the force applied by air to the object. So we apply the Newton's third law in the end and get the exact answer. So that's basically the idea of this question.
So I've got a question about how to find the back one.
So how to, continue.
So the front force for the inlet force is equal to H times L times V times U.
Yeah. So that is the mass flow rate. You also need to time another U to get the momentum. Since at the inlet, the flow is uniform, so it's U0 everywhere. So as long as you have the mass flow rate at the inlet, you can directly time it with the U0 to get the momentum at the inlet. Yeah.
So what should we do again to get the outer value, the output value?
The outlet is a little bit tricky because it's a profile. It's no longer a uniform outlet. So here we can assume, assume a tiny dy. So let's go from the very beginning. Since it's symmetric, so we can only consider half of it. Oh, sorry. So since it's symmetric, so we only consider half. So we only consider this half. All right. So for the top half, for an arbitrary, we find an arbitrary dy. So that's very tiny bit. We first need to know the velocity at this point. So the velocity at this point, as we said, is half u over L times y plus half u0. So since this is linear, we have the point here as y equals 0, u equals half u0, and at this point we know y equals L and u equals u0. So the linear relationship is very easy to get. So we get this relationship, and this is the velocity. So what we do is actually we integrate that velocity along the y. So that is what we get and then we time with density and width, and we get the momentum. Is that clear? Cool.
Actually, wait, so what you just said right now is being recorded, right?
Yeah, I think so.
Oh, it's just because
Yep.